right, so this question is from 2019, and I think I know why so many kids asked about this problem, because it's talking about the object's center of mass. So the center of mass of the two block system. So I think a lot of kids get to that and they're like, what the heck is it even talking about? So what I want to do before we tackle this problem, I want to do like some background explaining. Okay, so the background info that you need to know. So number one, I'm going to go through these and just follow along with what I'm saying. Okay, so first idea here. Number one, all objects have a center of mass, right? So like, look, you got a block right here. So an object center of mass for a perfectly symmetrical object, the center of mass is going to be like smack in the middle. There's the center of mass. Now, if you come up to this object and you exert a force on the object and there's no force to cancel this force, the object's going to accelerate. You know, this block is going to go faster, 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 faster. And in fact, if we graphed that, if we exerted, and by the way, I just want to point out this force right here, this is what we would call an external, how do you spell external? External. This would be an external force on the object. This will be important. Just keep following along. That's an external force on the object. So if we did a graph of velocity versus time, if that force were constant, what would happen is the velocity would gradually increase. And in fact, the slope of this would be the acceleration, right? If you take the slope of a velocity time graph, you know, slope equals rise over run. The rise is change of velocity and the run is time. And you're like, oh, the rise is change of velocity. That's the definition of acceleration right there. Okay, let's go to idea number two. So idea number two is a system of two or more objects will also have a center of mass. So I'm kind of leading up to this problem here. So say we got block A and then a block B right here, and say they're the same exact mass. If they're the same exact mass, the center of mass for this system, and by system I mean like we're considering the two of them together. So I'm gonna like draw a little like dot, 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 dot. Like that is our system right there. So if those blocks had equal mass, where would the center of mass be? Smack between them, right? The center of mass would be in the middle. What if block B had more mass than block A, right? So let's say you got big block B. Well, if block B had more mass, then the center of mass would be closer to block B, right? So you can talk about the center of mass of a system of objects, just meaning more than one object. Okay, third idea, a system's center of mass can have a velocity. So again, well, I probably shouldn't have erased that. So let's go back to this. Block A, block B, that's supposed to be a flat surface. Pretend it's flat. Block B, no hill there. Darn it, Swaldo. That's flat hill, flat surface. Okay, so say we got two blocks and say block B is at rest, right? It's just sitting there. And then let's say that block A has a velocity, right? So if these two blocks had equal mass, the center of mass would be right in the middle, right? Now, if block A were moving, would this center of mass still just be sitting here and like block A is going to crash into the center of mass? If block A were moving to the right, then the center of mass would also be moving to the right. Does that make sense? You know, so if you have motion within the system, you know, and again, the system is like block A and B together. The point is that a system center of mass can have a velocity. All right, number 4, the velocity of a system center of mass. Now this is important. It can only change by applying an external force to the system. So this center of mass for this little situation that I made up, we got block A moving and block B is at rest. The velocity of the center of mass, which by the way is not the same as the velocity for block A, right? Which will become clear when I get to number 5. This velocity of the center of mass can only change if there is some external force external, that's applied from outside the system, right? So what would that be? That would be, you know, somebody comes along and like pushes block A or pushes block B, or there's friction, right? If there were friction, friction would be an external force, and that would change the velocity of this center of mass of the system, right? But if there was no friction, dude, if there was 0 friction and 0 external force, if there's no external force, no friction, the velocity of the center of mass, this is going to be constant. All right, now number 5, in a collision, the force of the collision is internal to the system. So let me revert this one more time. I don't know, I just want to redraw it. So again, so let's say block A crashes into block B, and I promise you this is all going to be relevant to the problem when we get to it. So, you know, the center of mass is in the middle if they're equal mass, and then let's say block A is moving, right? So you're like, oh, if block A is moving and block B is just chilling here, well, block A is not going to crash into the center of mass. The center of mass will have a velocity also, which is separate. Let's call this one, let's call this V initial, and we'll call this velocity center of mass. So here's what I'm getting at. If there's no friction, so that just to ensure that there's no external force, no friction of any kind, block A smashes into block B. So what's our system? I'm going to draw around the system. So like this dotted, 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 dotted. This is the system we're focusing on. If block A crashes into block B, there's going to be a force there, right? When A hits B. But is that an external force? Did something come in from the outside and like, boom, exert a force on the system? Nope. The force of the collision when A hits B, let me do this. When A hits B, what am I trying to do? This guy. So A is going to come and hit B. Bam! They smash into each other. That's going to be a force internal to the system, which means, did the velocity of the center of mass change as a result of the collision if the force is internal to the system? No, it did not. So then let's say that A and B stick together. So now here it is after the collision. Here's A and then here's B, and now they're cruising off with some final velocity. This final velocity is going to be the velocity of the center of mass before collision. And the reason why is the two have now become one, right? The two have become one, they move off together. And of course, how do you find what that final velocity is? Well, when there's a collision, you say momentum before collision equals momentum after. So what was the momentum before collision? Mass of A times V initial, which was velocity, right? Momentum is mass times velocity. And then after collision, what's the total mass? Mass of A plus mass of B times V final. So V final is going to be MA V initial over MA plus MB. The velocity got smaller. But this final velocity after the collision is going to be equal to what the velocity of the center of mass was before the collision. And the reason for that is there was no external force. The only force present here was the force of the collision itself. So with that in mind, let's go to the problem, and then you guys can ask questions at the end, but this video is already getting long. So let's go to the problem. Okay, so if you're just tuning in now, this might not make a super lot of sense. So hopefully my little explanation was is going to shine some light here. So they set up this whole situation. So let me refresh myself. So we got 2 blocks, 1 and 2. The surface is frictionless, except for this region right here. There's friction right there. And by the way, so is friction going to be internal to the system? Our system is going to be 1 and 2 together, right? So like 1 and 2 together, where would be the center of mass for that system? If they're identical blocks, the center of mass is going to be smack in the middle. That's going to be our center of mass. So then block 1 is pushed with this force, constant force, that's important, a constant horizontal force. The plunger pushes block 1. Upon reaching point B, block 1 comes off the plunger and continues moving along the horizontal surface towards block 2. And then eventually block 1 collides and sticks to block 2 at point E. Okay, on the axes below, sketch the speed of the center of mass, you know, and this definitely is, like when they ask center of mass questions, it definitely is challenging. But again, keep in mind that, you know, what do we mean by center of mass? Well, we have 2 objects here. Our system is the 2 of them together. If they're equal mass, the center of mass is in the middle. Okay, so block 1 is gonna be given a velocity. So if block 1 is moving, is it just gonna crash into the center of mass of the 2 objects? No, the center of mass is also gonna be moving to the right if block 1 is moving to the right. Okay, and then block 2 is sitting over there at rest. So it's gonna start out like this. The center of mass, so if the plunger pushes with a constant force is gonna lead to a constant acceleration for block 1, right? Because F equals ma. If the force is constant, the acceleration will be constant. So between A and B, so from time A to time B, the velocity of the center of mass is going to go, let's just put it up to here. It's going to go bigger, 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 bigger. And this should be a straight line because basically here we have velocity versus time. And the slope of that is acceleration, and it's a constant force, so constant acceleration. Now, at point B, that's where block 1 comes off this plunger. So from B to C, in this region here, block 1 is moving with a constant velocity, which means, you know, the center of mass is still going to have a velocity, and that's going to be constant, moving to the right. Block 1 is not going to smash into the center of mass. So the velocity of the center of mass is going to go to a constant velocity like that. Now, at point C, we have friction. Friction is an external force, right? It's a force from, so again, our system is this, and friction is like this force that's acting from the outside. It's acting from the ground onto block 1, which is part of the system. So that's going to cause a decrease in velocity for block 1, which is going to cause a decrease in velocity for the center of mass. So the center of mass, you know, if the frictional force is constant, you know, there's going to be a constant deceleration of the velocity of the center of mass. Okay, and that takes us to point D. Now, from D to E, we're back to constant velocity, like that, no friction. And then at point E, so block 1 is going to smash into block 2, but the force of that collision, is it external to the system or is it internal? The answer is it's internal, right? So this is not the force of the collision. It's not a force coming in from the outside acting on the system. So what that means is the velocity of the center of mass does not change, and it just keeps going like that. So the two stick together, 1 and 2 stick together, and they move off with the same velocity that the center of mass had between points D and E. So that's the graph for part A. And the suggested time is 13 minutes, and I've probably already doubled that. So let's go to let's finish it, and we'll see if there's any questions. Okay, so here's the next question. So now they get into angular momentum. Okay, the plunger is returned to its original position. So now we have a ball, and this ball can roll. But I want you to notice there's no friction here, no friction between A and C. Between C and D, there is friction, and then we're back to no friction between D and E. So there's friction between C and D. The sphere is pushed by the plunger from point A to point B with a constant force that is directed towards the sphere center of mass. The sphere loses contact with the plunger at point B, and the sphere continues moving across the horizontal surface towards point E. All right, so we're here to the question. In which interval does the sphere's angular momentum, so let's just hit pause for a second. Angular momentum, let's start by talking about regular momentum. Just think about a block moving. Here's a mass M moving with velocity V. Regular linear momentum is simply mass times velocity. Now, angular momentum has to do with rotation. So here is a wheel, and there's the center right there. What angular momentum is, the symbol for angular momentum is L. Now, when you switch from linear situations to rotational situations, mass, which is a measure of inertia, I can't spell today. Inertia. Oh my gosh, it's too late in the day. So mass is a measure of linear inertia. It's the ability of an object to resist a change of motion. Well, rotating objects also have inertia, but it's a little more complicated. So what we have is what we call rotational inertia, which has the symbol I. And rotational inertia, it's some variation of mr squared, depending upon, is the mass all on the perimeter, like a spinning wheel, or is this a disk where there's mass throughout? The equation is going to be some variation of mr squared, but just realize when it comes to rotational inertia, mass is not the only measure. It's also the distribution of the mass. So M became rotational inertia, and then velocity becomes angular velocity. So back to this problem. In order for this ball right here to gain angular momentum, for it to gain angular momentum, there has to be an angular velocity. In other words, this thing needs to start spinning. It's got to start rolling. Now, what causes a spherical object to go from having zero angular velocity, because it starts out with zero angular velocity, to having an angular velocity, something greater than zero? What's going to cause, and by the way, that's called an angular acceleration. If you have a change of angular velocity, that's called an angular acceleration. Well, what causes angular acceleration? The answer is torque. Torque, so to relate this back to linear, so we did this for momentum. For linear, you could say like, oh, this object accelerates. We're going to talk about F equals ma. So there's that equation. For rotational situations, if you want something to start spinning, you have to apply a torque. And the torque equation is I alpha. So what I'm getting at here, in order for this ball to start spinning and therefore have an angular momentum because it has angular velocity, there has to be a torque. From A to C, there is absolutely no torque applied because there's no friction here, right? The ball is not going to start rolling because it cannot interact with the surface to get that required torque. Now, once the ball reaches point C, there's friction, right? And friction is going to exert a force this way. Let me see if I can draw that, right? So there's the force of friction, and that's going to provide the torque to cause this sphere to start rolling and therefore gain angular momentum. Okay, so what the heck is the question? Does the sphere's angular momentum change? Wait, in which intervals does the sphere's angular momentum change? The answer is only here, only from C to D. I did more than briefly, but what you would say is, you could simply say, in order to gain angular momentum, there must be a torque applied to cause an angular acceleration, and friction provides that necessary torque to gain angular velocity, or something like that. Is that the end? I think so. All right, you guys have any questions on that? No questions? Okay.